if m is an integer and n is a positive integer, then there exist unique numbers q and r such that m is equal to q times n plus r. R is the remainder, q is the quotient, and r lies between 0, could be r is bigger than or equal to 0, and it's less than n. So in the example we just saw, m was 23, n was 7, the quotient q was 3, and the remainder r was 2. Now, let's give the proof. So the first thing when you write down a proof, good practice, is to write down what we know. In this case, m is an integer, and we're taking n to be a positive integer. I'll say a little bit more about why it's positive in a few minutes. So, there are two possibilities. Either m is a multiple of n, or m lies between two successive multiples of n. So here, if m is a multiple of n, then we have the situation where m is equal to qn for some q, and if m lies between two multiples of n, as in this case here, then we have the situation where m is equal to qn plus some remainder r, which in fact must be equal to m minus qn. So stating that a little bit more carefully, we have that either m is equal to qn for a unique q, in which case m is equal to qn plus r with the remainder 0. So that's one case. And the second case is where m lies strictly between two multiples of n, which we've called qn and q plus 1n for some unique q. And then we can write m is qn plus the remainder r, qn plus r, where r is equal to m minus qn. So from the diagram, we certainly see that 0 is less than r is less than n. R lies strictly between 0 and n. And this can be checked with a little bit of algebra. So let's do that. So we have in the second case that qn is less than m is less than q plus 1 times n. So if we subtract qn from each term in there, we will get 0 is less than m minus qn is less than, when we subtract qn from here, we're going to get just n. So just with a little bit of manipulation of inequalities, we have that m minus qn, which is r, lies strictly between 0 and n. So in either case, we have that m is equal to qn plus r, and r now can be 0 or lie strictly between 0 and n. So r is bigger than or equal to 0 and less than n. And from the proof, q was uniquely determined by m and n. Remember, q was that number such that m lay between qn and q plus 1n, or was equal to qn. So q is uniquely determined by m and n, and hence so is r, since r is equal to m minus qn. So let me just say a little bit about the proof. First of all, it's a little unsatisfactory in some ways, because what we're doing here is we're assuming properties of the less than relation, which are hardly any, or I should say the result of the theorem is hardly less obvious, much less obvious than the properties we're assuming of the less than relation. If we were going to give a rigorous proof, we'd have to write down some axioms for arithmetic and show that everything else follows from these. Later on, however, we're going to give some much more interesting and non-obvious results in which we'll be deducing the result from some basic elementary properties, the sort of properties you've always used. one last comment about the statement of the theorem. We assumed that n was a positive integer. There is a version of the theorem which is very similar in case n is negative, but it's not particularly interesting, so we won't bother doing that here. And also I should note that if n is 0, then nothing very interesting happens because we cannot divide one integer. We cannot divide an integer by 0.